Hi, this is DeAnn Presley from Kansas State University. I'm a soil management extension specialist, and I've done a lot of work over the years on cover crops. And I was asked to speak on this topic of cover crops and crop nutrients. So was recorded in winter of 20. This is January 17th of 2022. And so it's during a time of just rapid price fluctuations for fertilizer, especially nitrogen fertilizer. So that's kind of the context here. And a lot of this input I got from Peter Tomlinson from research he's been doing with other people. So my head out of the way here. So cover crops, why are we talking about this? So cover crops, our adoption rate in Kansas is probably somewhere over 5% of cropped acres are having cover crops planted on them. So not everybody's adopting yet, but it is something that's increasing in popularity, up from maybe 3% a few years ago. So up 5%, and it could be higher by now. We do the census of ag every 5 years. And so once we have the next set of data that'll be taken actually in 2022, we'll know what those numbers are. But cover crops have been an important tool in sustainability, so used to enhance the sustainability of cropping systems. So with using cover crops, a lot of research has shown we can improve soil quality and soil health. We can reduce environmental pollution problems coming from agriculture. So stopping erosion, if we stop the loss, or not stopping necessarily, but reducing soil erosion. So less water leaving the field will carry less sediments, carry less everything else traveling along with those sediments, such as nutrients, such as phosphorus. Cover crops, if they're growing and using crop nutrients, then they'll help with nutrient leaching to reduce nutrient leaching through the soil profile, especially nitrogen, of course, and can help potentially with enhancing nutrient cycling, and that can help with reducing nitrogen losses as well. So some of the things we'll talk about here are growing it. So legumes fix atmospheric nitrogen. Everybody knows that. It's an important tool, obviously used by organic producers. They're going to do this in a very intentional, planned way to have legumes grow a lot of their nitrogen. You can bring it back up. So on sandy soils, especially any cover crop, but especially those ones with deep roots, can be used to scavenge nitrogen and keep it from leaching from the soil profile or going down and getting it from deep in the profile where maybe it's accumulated a little bit. You can keep it so cover crops can slow runoff to deterring sediment-bound nutrients from leaving the fields as easily, and speeding it. So again, nutrient cycling. And this is the one that we know maybe a little bit less about, but how will a greater diversity or more microbes in general lead to more rapid nutrient cycling? That research is very much ongoing. People are curious about that answer. So I want to talk about this research done by Craig Roseboom at Peter Tomlinson. So it's a long-term project, no-till. There's wheat, sorghum, and soybean in the rotation, and then cover crops, or the variable here is where we're putting cover crops, goes in here between the wheat and sorghum. So the choices are chemical fallow, so no cover crop, of course, double crop soybeans, so as a cash crop themselves. Summer non-legume is a sorghum Sudan grass. So it's not baled and it's not grazed. It's left to stay on the field. So from a research perspective, to study these nutrient dynamics. And then there is a summer legume, which is a forage soybean. So again, not removed in any way from the field, just grown for nitrogen. Winter non-legume is a radish, so daikon radish. And then a winter legume is crimson clover. So the crimson clover has been doing better in the past few years. Seen it a couple times recently, and it's, it got to be about maybe not a foot tall, maybe 8 inches tall or so, but really, really thick. So it's not a high biomass producer, but it is it's doing pretty well. So here are some of the data from the years. And one of the points I wanted to make here is that it's variable. What we grow every year is a little bit variable. So there's 2013, 2014, and 2015. And here, so if you look at the summer legume in 2013, we didn't have a lot. That was 0.6 tons per acre versus the summer non-legume, that'd be the sorghum Sudan grass. That was 2.6 tons, so more what you'd expect. But then let's just drop down and look at 2015. The summer legume grew 3.4 tons versus 6 tons for the summer non-legume, sorghum Sudan grass. So that's more typical what we'd expect. The winter legume, the crimson clover, grew 1.3 tons and the winter non-legume, the radish, 0.7 tons. So then nitrogen content has also been analyzed in that above ground material, not the below ground, but the above ground. And so how many pounds per acre? So the summer legume, this is the nitrogen content of the biomass itself, 42 pounds for the summer legume, 88 pounds in 2014 for the summer legume. And again, now I want to take it down to 2015, so the highest biomass producing year of these 3 years that are being shown. The summer legume had 256 pounds of nitrogen content, and that's in its own tissue. The carbon to nitrogen ratio is something interesting that to think about. So one of the other things I do is composting research, composting extension work. And so if you're thinking about composting, usually if you're designing a composting mix, you design about 30 to 1. Of course, this is different. It's above ground. It's not the exact same, but thinking about how fast things decompose. And usually in a composting context, you're thinking about 30 to 1, 30 parts carbon to 1 part nitrogen leads to controlled decomposition. If you have high carbon to nitrogen, so 60 or 80 parts of carbon to 1 part nitrogen, that's going to decompose slow. There's just not enough nitrogen to go around. But you see here for the summer legume, 14 to 1, winter legume, 17 to 1, winter non-legume, radishes, 17 to 1. Those are all narrow C to N ratios, which means that those will decompose very rapidly, which, from a cropping systems perspective might be good. So we get the nitrogen back into the soil, but how much of that is just decomposing on the surface and going back into the atmosphere? Not really sure about that. So of course, the real way to figure out how these are doing is to look at what are the crops afterwards. So it's the sorghum crop coming next. And so let's look at that. That's the point, is to determine how the legacy effects of the legume and the non-legume summer and winter cover crops between wheat and sorghum impact the nitrogen availability in the cropping system and the yield response of sorghum to nitrogen fertilization. So there is a nitrogen rate as well in here with 0, 40, 80, 120, and 160 pounds of nitrogen per acre applied, 28% UAN, subsurface banded, straight flat Coulter liquid fertilizer applicator, and this is applied following the sorghum planting. So one of the interesting things to think about is how are cover crops changing the soil? And so soil total carbon in grams per kilogram. So this is also the same thing. If you put a decimal point in here, so 20 would be 2% total carbon. And this particular soil here, this is I should have said this a long time ago. This site is near Manhattan, Kansas. So it's 34, 35, 36 inches of annual rainfall, not a calcareous soil. So there's no carbonates in the soil profile. So total carbon is the same as organic carbon in this case. We didn't have any inorganic carbonates in here. So you can see here that, first of all, at this sampling time, there was no significant differences in organic carbon at any of the depths. These are in centimeters. So this is probably 7.5 centimeters, 15 centimeters, maybe 25 centimeters. But at any of these lower depths, there's no differences in carbon. So let's focus up here on this upper depth. So probably the 0 to 7.5 sampling depth. So 0 to 3 inches. And there is a significant difference. So the chem fallow, the one with no cover crops, has the lowest carbon, which is what we would have expected. And the one with the highest carbon is the one that produces the greatest biomass. The greatest amount of above ground biomass is what we would expect to be leading to the most amount of below ground biomass roots as well. And so that ends up having the greatest amount of carbon. So we've sequestered some carbon here. So some rough math, it looks like 1.94% for the chem fallow versus maybe 2.1 something percent for the sorghum Sudan grass. So that's a difference. And if we wanted to trade that carbon, we'd have to know the bulk density. You'd multiply the thickness of that layer times the bulk density times the percent soil organic carbon, and then you could compare how many tons difference these treatments are, and that is happening in this study as well. So then, of course, nitrogen response. How is the crop responding? And you can see in this picture, you can see that there are some differences in the greenness of the crop. You can definitely see that the plot boundaries here for this plot, the plot boundaries for this plot, the plot boundaries for this plot. So those are, I'm going to guess, those are probably the zero or low nitrogen amounts, but still. And so then this is measured. So the yield, and this is the 8-year average for the sorghum response to cover crops, the 8-year average, 2009 to 2016. And so you can see this is the rates of nitrogen fertilizer. So the 0, 40, 80, 120, and 160 pounds of nitrogen per acre. And then the yield ranging anywhere from a low of a little under 60 to over maybe not quite 120. So that's the yield range we have on this particular study. And so the line that comes out down here, the lowest, is the summer non-legume. So that's the sorghum Sudan grass left there in the field, not harvested off in any way, just left there in the field. The chem fallow is this dark line, and it's somewhere in the middle. So of course, this difference between the black and the red is really the amount of immobilization that's happening. So as the microbes are using any of the nitrogen in the system to break down the biomass produced by all of that sorghum Sudan grass, of course, the result was higher organic matter, which is, it could be a goal for some people. That's a good thing. But that, you can see that the difference in nitrogen use then at these lower rates particularly. So then you can see up here, this box that's drawn around here, this is a summer legume. So the forage soybean is one of the highest yielding, and it's starting to rise above the other lines. And yeah, so this is, I'm going to skip that one. So here's the thing here I might be drawn to right away is the nitrogen fertilizer replacement value. So 33 cents per pound of nitrogen. That was when the slides were first made a couple of years ago. And I do have maybe a more realistic price for nitrogen. Of course, this number is rapidly fluctuating, so I'll come back to that. I'll start with this slide with the 33 cents per pound. So this is the nitrogen fertilizer replacement value, sort of, which is really the point of this study. It's what are we getting out of these cover crops? And so this is the mean grain yield at 0 pounds of nitrogen rate. And so you can see chem fallow is 88 pounds or bushels per acre. And I'll start with the high one. So summer legume, forage soybean, that's got the highest yield. So of course you're growing nitrogen in this one, growing the most nitrogen in this one. You can see then you might think about, what about that winter legume? What did that get us? Well, that's grouping in the second one. So where it's followed by the A, that one stands alone. It's by itself. Any of these treatments with a B behind them are similar to each other. They all yield the same statistically. So chem fallow, double crop soybean, winter legume, and winter non-legume are all in that B category. So the lowest yielding one at 0 pounds of nitrogen is, again, that summer non-legume, which is fine. So then what are our credits if we have any? Well, the ones that get the most credit would be summer legume has a credit of 30 pounds per acre of nitrogen grown from those forage soybeans. And then the double crop soybean is similar. So it's in its own category of 8 pounds of nitrogen per acre. And then winter legume and winter non-legume, they actually have negative numbers. So statistically, they group with this other one. And you can see the summer non-legume, of course, is using nitrogen. And that's, of course, because its microbes are using nitrogen out of the soil because they're not getting it out of the tissues much. They're using it out of they're using it, and so it's not available to the next crop. So this, if you do the math, and at 33 cents a pound, this is what the numbers look like. So let's bump it up here to the 90 cents per pound nitrogen. So summer legume, in 33 cents per pound, 9.9 or $9.90 credit, but that number looks more attractive at a higher fertilizer nitrogen price, which is, of course, the point of this talk, is to say that some of these things make more sense economically to grow nitrogen versus buy nitrogen, depending on what the prices are. And yeah, so management implications. So cover crop selection and nitrogen management are going to impact sorghum productivity. They have done that. And there's a potential to replace a portion of the cash crop nitrogen requirement with the summer legume cover crops. So 30 pounds of nitrogen per acre coming from those late maturing forage soybeans. And high C to N ratio cover crops such as sorghum, Sudan grass would require additional nitrogen input. Of course, it was the most effective way to build soil organic matter too. So although there was no significant improvement on the nitrogen supply with winter cover crops, there may be other potential benefits, such as reducing potential nitrogen losses if they're sitting there using it versus, using it, maybe producing a little rather than just losing it outright. But the end rate to optimize the sorghum yields in this 8-year average was summer non-legume using 120 pounds of nitrogen per acre versus other cover crops and double crop soybean was 80 pounds of nitrogen per acre. So again, that summer non-legume growing sorghum Sudan grass, although it built soil organic matter, it needed the most nitrogen for the following sorghum crop versus other cover crops and double crop soybeans, we needed 80 pounds. So the next thing I'm going to talk about is legumes and nitrogen production. So this Midwest Cover Crops Council selector tool, and this has a Michigan State University email address or website address. This MCCC is a consortium of a whole bunch of people that are university types and industry types and regulatory type people that all come together to say, what do we know about cover crops and what can we do with that information? And so one of the best pieces that they've done is this selector tool. There's lots of great resources as well. Each state has their own information up here, but this decision tool just gets a ton of use because it is so useful. And so if you go here to this tool, so you can start, the first question is, where is your farm? So what state? So I chose Kansas, and then I chose Ellsworth County. And then you choose your goals after that. So I just think of this like if you're going vehicle shopping, you'd walk into the dealership and you talk about what your goals are for, do you want to haul stuff? Do you want to haul people? Do you want to go fast? You talk about what your goals are. And it's the same thing with cover crops. What do you want to do with them? And then here after that, then you show your cash crop rotation. So are you wanting to put this between wheat and sorghum or wheat and corn? Or is this going to be a winter crop after soybeans or something? You would put all that detail in, and so then it'll show you, it has this list. We have over 40 different cover crops for Kansas that we know something about, that we've rated. And so that's what these next slides are about, is just focusing on the nitrogen today though. So we've rated everything with a 4, 3, 2, or a 1, or even a 0. So I'm just going to show you the 4s, 3s, and 2s for legumes on our list. So the first one up, these are all the 4s. So cowpeas, of course, those are a summer crop, have a similar growth habit to soybeans. They could produce anywhere from 10 to 80 pounds of nitrogen. And so that's a huge range, right? That's the first thing I want to say is the ranges on all these numbers are huge. And that's because it depends on how fast you got them planted, how well they inoculate, or how well they nodulate. And so you have to get, of course, and your seed salesperson will sell you the inoculum for all of these things as well. You have to get the right inoculum for the cover crop that you're going to plant. So have to get it treated, have to handle the inoculum correctly, of course. So cowpeas, if you plant these with a really, really short window of time and they don't get very big, then you're going to be more on the 10 pounds. But if you plant them early in the summer and they get tons of growth before you terminate them, you could be more like that 80-pound rate. So I think for most people, some number in the middle of that is what you're going to get, unless you plant them super late, then you're going to be on the left side of the range. So sun hemp is one. We had a long-term study that was done in central Kansas with sun hemp, and sun hemp is a good one for Kansas. It loves the heat. It does get pretty big, and when it gets big, the stems can get pretty tough. So, that's one I wouldn't let that one just get huge. But sun hemp is a legume, and so anywhere from 20 to 120 pounds of nitrogen, or somewhere in the middle, probably is what's realistic for us. Sweet clover, 5 to 50 pounds of nitrogen. Is a potential range, and hairy vetch is a winter cover crop. So it can grow anywhere from 5 to 100 pounds of nitrogen. So The bigger it gets, the more pure the stand is of any one of these cover crops. So if you grow a solid stand of hairy vetch, you're going to get a higher amount of nitrogen than if you grow it in a mix with cereals or something like that. So then these are all of our threes, the things that we rated as a 3. So mung beans, 10 to 80 pounds. I've never seen anywhere close to 80 pounds for mung beans, honestly. Red clover, 5 to 100 pounds of nitrogen, probably somewhere in the middle. Spring pea, the researchers that I've talked to that research field, Springfield pea, are like, it's not anywhere close to 50. It's a lot more like 5 or 10 pounds from a Springfield pea. Winter pea, also 5 or 10 pounds is probably more likely. Now you can get to these higher side of the ranges if you let them grow. If you give them the longest window possible and let them get really, really big, you plant them really, really early and you let them grow really, really long, you're going to get the max amount of nitrogen fixation. Not saying that won't crowd into your planting window for your other crops, which is why some of these high ends on the ranges are probably not possible. Soybeans, again, we said that our soybeans for our forage soybeans in the previous study I just got done talking about was more like 30 pounds. So that's what I'm saying, is somewhere in the middle of these ranges is what's actually possible for us in Kansas in a real cropping system, a normal cropping system. Chickling vetch, 5 to 50 pounds of nitrogen. Again, probably more like 5, 10, 20 maybe. Common vetch does a little better, probably somewhere in the middle of that range. And then these are our 2s. So this is a lower rating. Crimson clover, 5 to 70 pounds of nitrogen. And from our study, we saw that was more like a single digit number. So, and it just depends on how well you can grow crimson clover wherever you live. So it gets about 8 inches, 12 inches tall, maybe, and it is pretty lush and pretty thick, but it just doesn't put on huge biomass. And so we're on the way low side of that number. Guar is one I know a little bit less about, and actually that's why I think we gave it a 2 for a rating when we rated this. Is we're like, well, guar, it's definitely a legume and people grow it, but we don't have as much information on this. So guar has got a huge range. It's a summer one, so if you let it get pretty big, you probably could fix a lot of nitrogen, but I just have less information about that than other things. Spring and winter lentils are one I have grown, and I've just never gotten very large biomass off of those at all. They stay pretty small, and they're kind of a spindly plant. So I've just never seen much growth from them. And so again, I'm talking about above ground growth, and really what we care about is below ground, but they're related. And so if we have more big, lush above ground growth, there is a bigger root system underneath that fixing a lot of nitrogen. So you can relate it. And so again, spring and winter lentils, they are a legume, but they're not going to be fixing a lot of nitrogen. So the last thing I'll say is that this topic of how cover crops decompose and their nutrient release is still being very actively researched. So this is some of my own research plots this is near Mound Ridge in McPherson County this summer. And so here, this is a little solar panel with a little data logger inside and an antenna communicating to the edge of the field where we've got another device that transmits this data into the cloud. But these are soil moisture sensors that are underneath this, and there's moisture sensors and temperature sensors underneath these bags. And so what we did is this had a cereal rye cover crop, so we clipped it, right? The day the farmer wanted to spray it, we went out there ahead of time and clipped it in a known area to know how many tons per acre biomass we have. And then we put it into these plastic mesh bags, we staple them to the ground, and then we pick those up every so often. And we pick them up every 2 to 4 weeks. So 2 weeks at the beginning of the season, and then every 4 weeks later in the season. And we're analyzing those right now for carbon and nitrogen and ash. And we already know the mass of the biomass that was still in the bag, and the soil temperature and moisture data. And that's being used to develop and refine nutrient availability models. So that work is still very much ongoing. And then, of course, as I said, the microbe information that people are collecting right now and how that is affecting availability of nutrients, that's still very much ongoing as well. So there's my contact info. Happy to have this talk with you at any time, or we can talk via Twitter too. But thank you very much for your time and attention.